Creating a stem and leaf plot. Section 2.2, more graphs and displays. So the stem and leaf plot is the primary graph that we're going to discuss here, and then just highlight a couple other graphs that might come up. So in a stem and leaf plot, each number is being separated into what's called a stem and a leaf. It's similar to a histogram. If you turn your graph on its side, you can kind of see like the height of the bars. And it still contains the original data values. So in the little image off to the right, this is your stem. These are your tens place or your hundreds place. And then next to it is your leaves. Those are your ones places. So if you look within these numbers, you will see the number 21 when you put them back together, 21. Then 25, it's the 2 with the 5. And then 2 with 5 again, because there's a data value that repeats, 26, 27, 28, and so forth. This is a quick way to sort data, smallest to big, and also see patterns in your data. So this example, it says the data set lists the number of text messages sent one day by 50 cell phone users. Display the data in a stem and leaf plot. Describe any patterns. So the quickest way to do this is to identify your minimum and your maximum so you know how big of a graph you need to make. So it looks like our minimum in here is 16 and our maximum is 149. So we're going to squeeze in a stem and leaf graph in here. Our smallest stem is then the tens place. So to write the number 16, we have a stem of 1 and a leaf of 6. Now, if we scan through the rest of our numbers, it doesn't look like we have anything else in the tens. So then our next stem would be the number 2. And we do not skip any stems. We put all numbers here. So I can go ahead and pre-label this. All the way down to 14, because that's where the 149 is. None of our stems are going to get skipped, no matter what, whether we have a number for that row or not. So now we can kind of start filling it in. And at this point, you can just go down the column. So our first number over here is 76. Find the row of the 70s, and you can fill in a 6 to the right. 122, find the row with the 12, and place in the 2. And we can keep on going through the list in this manner. You might notice in the homework, it might ask for your leaves to be in smallest to greatest. So you can always put all of your numbers in there and then go back in and just reorder them quickly to match. That is a requirement done by my stat lab. Just makes it nice and visually appealing. The other thing you might notice as we're kind of going through these numbers is you want all of your numbers to kind of line up so that you have even spacing, similar to how we were doing the dot plot and all of our dots were evenly spaced and the same distance apart. Same thing with our leaves. You want them to all line up. Notice as I write the number 34, all of these leaves are stacking up between my 20s and my 30s. And depending on your data set, it takes a little bit of time. A useful tool for this is to practice typing your data into your calculator, and then you can sort the list smallest to big, and that might help you quickly find the numbers that go in each one of these rows, as opposed to doing it kind of out of order like we are currently doing it. And it would give you an opportunity to just practice using your calculator, typing in data, doing things with the calculator like sorting a list. We're almost there. And if you're waiting for a shortcut for this, there is no shortcut. You do just have to go through the motions, get all of your data in there. When you are done, I always recommend you kind of go back over and make sure you count all of your leaves, make sure you didn't skip any numbers. And we do have our last one in there. So we are all set. We've got our stem and leaf. And notice there's nothing in that 13 row. You would just leave it blank. You do not put a 0 in there because otherwise that would represent a number. So if you have a row that's blank, that's totally fine. Now, the other thing that might come up is to split your stems. So instead of just having one row for each one of those tens places, you could split them. So what that means is for stem and leaves, especially when you have a lot of leaves in one row, you could split it where it's 2 stems of 1, 2 stems of 2, 2 stems of 3, and so forth. Now, what this would mean, and we just continue on, is that for the first row, your leaves are all 0 to 4, and your second row, your leaves are all 5 through 9. So that way there's the same number of digits split. So 0 to 4 is 5 different digits, 5 to 9 is also 5 different digits. So if we go back, 16, there's only one number in the tens, that would be, and then the second row, we'd put that 6. For my 20s, we had 26, that goes in the second one. 29 goes in the second row. 23 goes in the first one. 29 goes in the second row. 24 goes in the first. 29's in the second row. 26 is in the second row, another 29, a 28 in the second row, a 20 in the first row, and we've hit all of our 20s. Same with the 30s. Anything that has a ones place of 0 to 4 would go in the first row, 5 to 9 would go in the second row. And this is actually a good chance to kind of see these numbers lined up nice and orderly, so you can kind of see patterns a little bit clearer this time. Looking to see if we have, oh, we had a 19. So we had another one for our tens. 39, another 33. This is why I like having it printed, and I can slash off the numbers as I go so I don't miss any numbers. And so forth. You would be able to continue going through. So this just kind of helps spread out your data, especially if you had a lot of data concentrated in a small range of numbers. This gives you a little bit more bars and rows to look for patterns. So another graph you can make is a pie chart. Pie chart is a convenient way to present qualitative data graphically. So these are percents of a whole, each one of these sections. Keep in mind, percents all add up to 1. So all of those numbers should add up to a 1 as a decimal. So a circle is divided into sectors that represent categories. Here it mentions qualitative. Those could also be number categories. So like an age category of 20 to 29, an age category of 30 to 39, and so forth. So the area of each one of those sectors is also proportional to the frequency of each category. What that's leading us to is the fact that each one of those can be found by a relative frequency. So the frequency divided by your sample size. So here's our example. The number of earned degrees conferred in thousands in 2014 are shown on the table. Use a pie chart to organize the data. So we have our 4 categories: associates, bachelor's, master's, and doctoral. And we need to add these up so we have a total sample size here. So if we're adding up 1003, 1870, 754, and 178, We get a sample size of 3,805. So in order to make a pie chart, we need our relative frequency. So that is the F over N. Each one of these numbers in thousands are our F values. So we're going to take, for the first row, the 1,003 divided by our sample size, 3,805, and we're going to round our decimal to 0.26. Then for our second row, we're going to take 1870 divided by our sample size, 2 decimals, 0.49. And repeat this down the column. So each frequency divided by sample size, round it to 2. Watch your rounding here. Now, like I mentioned on the previous slide, all of these decimals should add up to the number 1. You could also switch all of these relative frequencies very quickly into a percent just by moving our decimal point or taking each one of those decimals times 100. So this is the percent of our pie chart each one of those represents. So to make a quick sketch, I always start by putting the biggest one on there. So 49%, that's almost the full half, so a little less than a full. That is going to be our bachelor's category. I would mark it 49%. The next biggest chunk is 26, so that's like a quarter of it, maybe a little bit more. That would be our associates. That's 26. And then just divide up that little last bit into our 20%, which is our master's, and then the 5% left for our doctoral. So another graph you can make is a vertical bar graph called a Pareto chart, which is where the height of each one of your bars represents the frequency or relative frequency, but you have categories between each one. So similar to the data set we just had, where it was associates, bachelor's, master's, doctoral, those would be like the categories and then the height of a bar going down. The bars are each going to be positioned in order of decreasing height. So always the tallest one first, and then go down the row, tall to short. So here's an example. In 2014, these were the leading causes of death in the United States: accidents, cancer, chronic lower respiratory disease, heart disease, and stroke. Use a Pareto chart to organize the data. What was the leading cause of death in the United States in 2014? So we're going to squeeze this in here. We're just going to make a quick sketch. The big thing you're looking for is between these numbers, which one's the biggest? In this case, it's heart disease. So heart disease would be our first bar. Then we would have cancer. Then the next one would be the chronic lower respiratory disease. So we're going to abbreviate there, CLRD. And then we have accidents right behind that one. And then we have stroke. And I just made a quick sketch, but then on the right-hand side would be our scaling. So how many, and maybe you're counting by hundreds of thousands or by 50,000s, however you would like. But the big thing with this is the bars do not touch, and they always go in descending order. Another type of graph we can make is called pair data sets, where each entry in one data set corresponds to one entry in a second data set. So if you're looking at the graph and you're thinking of perhaps a college algebra course, you have an ordered pair. So each ordered pair has 2 different quantitative values. So we would graph these using something called a scatter plot, which we'll talk a lot more about in chapter 9. So this is just a brief introduction of the term. The ordered pairs are graphed as points in a coordinate plane, and they're used to show the relationship between two different quantitative variables. And later in chapter 9, we'll discuss things like correlation, the line of best fit, whether you can make correlations between them in causation. So here's just a brief example. It says a British statistician, Ronald Fisher, introduced a famous data set called Fisher's iris data set. This data set describes various physical characteristics such as petal length and petal width in millimeters for 3 species of iris. The petal lengths form the first data set and the petal widths form the second data set. So we have lengths and widths from this. As the petal length increases, what tends to happen to the petal width? So as our length gets bigger, what's happening to our width? And you'll notice there's a trend to this data set. It's going uphill. And in fact, I'm going to erase that line because later when we talk about line of best fit, we actually go through the dead center of all of our dots to make a line of best fit. So to answer the question, we would say the width increases. As your length increases, your width increases. Another type of graph we make is time series. Data set is composed of quantitative entries taken at regular intervals over a period of time. The big thing is that time is your x. So for example, the amount of precipitation measured each day for 1 month. Use the time series chart to graph. So here's an example. The table lists the number of motor vehicle thefts in millions and burglaries in millions in the United States for the years 2005 through 2015. Construct a time series chart for the number of motor vehicle thefts. Describe any trends. So this chart actually gives us more than what we need, because to do a time series, we need a year. We need some regular interval for our x-axis. We're going to put years across the bottom. And then what they want us to graph is just the motor vehicle theft. So this column here. So in 2005, because this is going to go in chronological order, over to 2015, our numbers are actually going down. So if our scale is counting by perhaps 0.5, we could make some pattern here as we're going, and what you'll notice is the dots tend to go downwards. So as the years pass, we actually had less and less motor vehicle thefts each year. That would be a pattern that we would be able to identify.